disconnect the multimeter from the battery by turning the rotary switch to position off. Let's start with resistance measurements using some carbon film resistors. The rotary switch has to be set to the desired range position for resistance measurement, marked by the Greek letter omega, which is the symbol of ohm, the derived unit of electrical resistance. When using the direct method of resistance measurement, a constant current generated by the internal battery is running through the test leads of the multimeter, and the voltage drop across the device under test is scaled to a resistance value. The available range positions are 2 megaohm, 220 respectively 2 kiloohm and 200 ohm. When determining the resistance of an unknown device, you should start with the highest range possible, which is 2 megaohm. The test series consists of fixed resistors with 1 megaohm, 220, 27 and 2.7 kiloohm, 390 and 10 ohm, a 1 megaohm potentiometer, and finally a piece of metal wire. The color code indicates the resistance value and the tolerance of the axial carbon film resistors. Let's start with the 1 megaohm resistor. After connecting the test leads with the metal terminals of the resistor, a value of 0.992 can be read on the display. Since the 2 megaohm range is selected, the measured value is 0.992 megaohm. The polarity of the testing voltage generated by the multimeter is irrelevant when determining the resistance of ohmic resistors, hence we get the same value when swapping the test leads. Before recording the value of the potentiometer, the device is turned to its maximum position and we get 0.871 megaohm. According to the labels, the resistance of those devices should be 1.00 megaohm, apparently it isn't. The reasons for the deviation will be treated some later in this video. For the 220 kiloohm resistor we get 0.219 megaohm, and for the 27 kiloohm resistor 0.027 megaohm. The rotary switch can be set to the 200 kiloohm range to get a more precise reading of the resistance value. Now the displayed reading is 27.0 according to a value of 27.0 kiloohm, which is more precisely because of the decimal place. When setting the 20 kiloohm range, a single 1 is displayed, indicating that the measured value is too large for the selected range. Always use the smallest range possible to ensure getting the highest precision of the reading. The resistance value of all other resistors is determined in the same way. The last device is a piece of wire with a diameter of 1 mm and a length of approximately 3 cm between the two test leads. We get 1.5 ohm, which is very high for this piece of wire. So let's join the test leads of the multimeter. The expected value is 0.0 ohm, but we get 1.0 ohm. One reason for this curious value is the contact resistance of the test leads, another one is the low precision of the multimeter when measuring low resistance devices. The next test series deals with different voltages. There is a 6V battery, a computer power supply with output voltages of 12, 5 and 3.3V, and finally an adjustable transformer of a model railway. Voltage is always measured between 2 points in a system. Usually a common reference potential such as the ground of the system is used as one of the points, and the black test lead is connected to that point. The difference in potential between the reference point and the potential at the tip of the red test lead is indicated by the multimeter. When doing voltage measurements, you have to know whether it is DC or AC voltage. The voltage output of the battery and the computer power supply is unidirectional, hence the rotary switch has to be set to that functionality. Before starting the measurement, dial the highest range available whenever an unknown voltage is tested. The rotary switch can be set to a lower range after connecting the test leads to the voltage source. We get a reading of 6.34 volts at the battery. When swapping the test leads, we get a value of minus 6.33 volts. In contrast to resistance measurements, the arrangement of the test leads matters when recording DC voltages. Because of the significance of the polarity, there are markings for the positive and negative terminal at the battery, and the displayed value of the multimeter is positive whenever the black test lead is connected to the negative terminal of the battery. Thus, the negative terminal of a battery is also named ground. The negative terminal at the computer power supply is marked by black wires, hence the black test lead should be connected to one of the black wires of that voltage source. Between the black and one of the orange wires we get plus 3.40 volts. Between the black and one of the red wires plus 5.10 volts. And finally between the black and one of the yellow wires plus 11.98 volts. Swapping the test leads results in displaying negative values. DC voltages are always indicated in reference to the potential at the black test lead. Thus, at the computer power supply we get a voltage of plus 1.69 volts between one of the orange and one of the red wires, plus 6.87 volts between one of the red and the yellow wires, and finally plus 8.57 volts between an orange and a yellow wire, respectively minus 8.54 volts between a yellow and an orange wire. Whenever a negative value is displayed, the negative pole is at the red test lead, otherwise it is at the black one. Before attaching an electronic circuit to a DC voltage source, you should check for the right polarity, or else the circuit may smoke up. At an AC voltage source, the output voltage periodically reverses polarity very quickly. At the transformer shown here, that occurs 100 times a second. When attaching the test leads to the transformer while the rotary switch is set to DC voltage, the displayed value isn't stable. We can read values around 0 volts, independently from the position of the transformer's actuator. That's the mean value of a sinusoidal AC voltage. Momentarily, the voltage differs significantly from 0 volts, ranging from plus 25 volts to minus 25 volts. Therefore, AC voltage is often characterized by the root mean square value. The RMS is a statistical measure of the magnitude of a varying quantity. That's all about the theory of root mean square for now. The AC voltage is rectified by the multimeter and the root mean square value is displayed. To enable that function, you must set the rotary switch to an AC voltage range. Now you can read the RMS voltage output of the transformer. As explained before, the polarity of the AC voltage alters very quickly and the multimeter rectifies that voltage, thus the value doesn't change when swapping the test leads. When doing measurements at a DC voltage while the rotary switch is set to AC voltage, the reading is significantly higher than the true value. Hence, you should always have an eye on the correct setting of the rotary switch. A difference in potential can not only be detected at a voltage source, but also across a device in an electric circuit. To do so, the multimeter has to be connected in parallel to the device under test. The circuit shown here is composed of a filament lamp, a diode, a 1 kΩ resistor and a battery. When connecting the multimeter in parallel to the filament lamp, we get a value of plus 11.55 volts with the positive terminal at the right side of the lamp. When connecting the test leads to the terminals of the resistor, we get an almost identical value of plus 11.52 volts, which isn't remarkable, because the resistor is switched in parallel to the filament lamp. Across the diode we get plus 0.82 volts, and finally the voltage output of the battery is plus 12.32 volts. When using a multimeter with the rotary switch set to voltage measurement, the device is also named voltmeter. The next functionality to be treated is current measurement. When using a multimeter with the rotary switch set to current measurement, the device is also named ammeter. There are 4 different ranges suitable for detecting direct currents: 2, 20 and 200 mA, respectively 10 ampere. To enable the range above 200 mA and up to 10 ampere, the red test lead has to be connected to the left jack of the multimeter. In principle, the current measurement is a voltage measurement. The current passes a resistor of accurately known resistance, and the detected voltage drop across the device is scaled to the accordant current value. The higher the current, the lower the sensing resistance must become, since the resistor in return affects the measurement, as we will see some later. For measurements above 200 mA, there is a wire strap placed between the middle and the left jack of the multimeter. That special low resistance path is named shunt resistor. The construction allows the current to bypass the tiny contacts of the rotary switch. Those thin strip conductors would not withstand currents above 1 ampere. To be able to measure currents, the multimeter has to be switched in series to the device or circuit to be discovered. The circuit must be opened to insert the multimeter. Same as for resistance and voltage measurements, the detection of a current should start with the highest range possible. Thus, the rotary switch has to be set to the 10 ampere range, and the red test lead must be connected to the left jack to enable the high current shunt. As soon as the circuit is reconnected to the battery, we can detect a current of 0.82 amperes running through the multimeter. The resistor and the filament lamp are switched in parallel. To be able to determine the current running through the resistor, the multimeter has to be inserted into the accordant leg of the circuit. We can read a value of just 0.01 ampere. Thus we can choose a lower range to get a more precise reading. In order to enable the lower range, the red test lead has to be removed from the left and reinserted in the right jack, and the rotary switch has to be set to the 200 mA range. After reconnecting the circuit to the battery, we get 11.6 mA. Thus we can step down to the 20 mA range. When doing current measurements, you should disconnect the circuit under test from the power supply before turning the rotary switch. During switching switchover procedure, the current running through the rotary switch of the multimeter is interrupted for a short span of time, which can cause high voltage peaks across the switching contacts if inductors are placed in the circuit under test. In the lower range we get a more precise reading of 11.49 mA. When doing direct current measurements, the polarity of the test leads is relevant. When swapping the test leads we get minus 11.50 mA. The current is running through the multimeter in the opposite direction. At this position of the rotary switch, the multimeter can determine a direct current ranging from 0 to 20 mA. Apparently it is yet indicating an alternating current. But remember the diode inside of the circuit. The current passes this device only in one direction, hence the current gets rectified. By inserting a second diode, the current can pass the circuit in both directions, and as expected, the indicated value is around 0 mA now. This multimeter has no built-in function for detecting an alternating current. Now that we have learned how to determine currents and voltages, we can do some indirect resistance measurements. The resistor to be discovered is attached to an adjustable direct current source with a maximum voltage output of 12V, which is non-hazardous to human life, and with the help of the first multimeter, the current running through the device is determined. With the second multimeter, the voltage drop across the resistor can be determined simultaneously. The ohmic resistance is calculated using Ohm's law. Once again, the carbon film resistors with 10 and 390 ohm, 2.7, 27 and 220 kilo ohm, as well as the 1 mega ohm device are used for the test series. At this arrangement of two multimeters, there are considerable deviations while examining high resistive devices. The inner impedance of a real voltmeter is high but not infinite, consequently an additional current is running through that multimeter, bypassing the resistor and being added up to the current running through the ammeter. We can measure that current with a third multimeter being switched in series to the voltmeter. While testing the 1 mega ohm resistor, a current of 0.012 mA is running through the voltmeter, which is approximately half the total current. When subtracting this value from the total current, we get 0.011 mA running through the resistor, and the calculated value is much closer to the expected resistance. The smaller the resistance of the device under test, the lower the leakage current, and when using the 390 ohm resistor it becomes negligible. If there are just two multimeters available, you can use another circuit. Of course, the ammeter is still switched in series to the resistor, but the voltmeter is by now connected in parallel to both devices. Yet there is still a current running through the voltmeter, bypassing the resistor, but that current is not detected by the ammeter, because that instrument is bypassed too. There is a considerable deviation while inspecting devices with a low resistance when using this arrangement of the multimeters. Like explained before, a current is detected as a voltage drop across an accurately known resistance placed inside the multimeter. That inner resistance of the ammeter is small, but never zero. Thus, there is an additional resistor switched in series to the resistor under test. By the voltmeter, the voltage drop across the ammeter is added up to that across the unknown resistor to be tested. The voltage drop across the ammeter can be measured with a third multimeter. This instrument is set to voltage measurement and it is placed in parallel to the ammeter. drop across the ammeter has to be subtracted from the value displayed by the first multimeter, by what the resulting resistance becomes more precisely. The voltage drop across the ammeter is 0.177 volts compared to a total voltage of 0.312 volts when testing the 10 ohm resistor. For the 1 mega ohm device we get a ratio of 1.2 millivolts to 11.48 volts, thus the voltage drop across the ammeter is negligible. When doing simultaneous measurements of current and voltage, circuit 1 is favorable at low resistive devices, while circuit 2 should be used when testing high resistive devices. Let's replace the resistor of the circuit by multimeter number 3 to determine the inner resistance of that instrument. At the first run, the multimeter is set to DC voltage measurement. Supposedly the inner resistance will be very high, for which reason measurement arrangement number 2 is useful. The resulting resistance is approximately 600 kilo ohms at the 200 millivolt range and 1 mega ohm at all other DC voltage ranges. Now the multimeter is set to current measurement to observe the impedance of the ammeter functionality with the help of circuit number 1. The resulting resistance is approximately 1.2 ohms at the 200 mA range, 10.3 ohms at the 20 mA range, and 100.6 ohms at the 2 mA range. When switching one multimeter to resistance measurement, we can determine the inner resistance of a second multimeter directly. We get 100.6, 10.6, respectively 1.5 ohms for the ammeter functionality at the 2, 20 and 200 mA range. When switched to voltage functionality, we get approximately 1 mega ohm at all ranges. There is a remarkable deviation from the indirect method at the 200 mV range. The same deviation was determined in the first version of this video recorded more than 1 year ago, thus I can exclude a measurement error. Make suggestions for those curious values. Let's check the voltage output of the multimeter when set to resistance functionality. A 6 kilo ohm carbon film potentiometer is connected to the jacks of the right multimeter, which operates as ohm meter. As soon as the left multimeter, which is set to DC voltage measurement, is connected in parallel to the potentiometer, we can read plus 0.213 volts at the display, hence the positive terminal of the ohm meter is at the right jack. The indicated resistance value is 6.14 kilo ohm. When lowering the resistance of the potentiometer, the voltage output of the ohm meter is decreasing, and at a resistance of 4.83 kilo ohm we get 0.177 volts and finally 0.147 volts at a resistance of 3.84 kilo ohm. We get a nearly linear correlation. The displayed resistance value in kilo ohm is approximately 27 times the indicated voltage. At small resistance values, the factor is decreasing noticeably to just 23, because we get a voltage of 0.079 volts at a resistance of 1.86 kilo ohm. We can determine a resistance of 1.86 kilo ohm at the lower range of up to 2 kilo ohm, hence we can read 1.854 kilo ohm at a voltage of 1.261 volts. The voltage was stepping up while setting the rotary switch to the lower range. The factor between the indicated resistance in kilo ohm and the voltage output of the ohm meter also changed after dialing the lower range. It is now slightly above 1. Now the multimeter is connected in series to the potentiometer, enabling the measurement of current. contrast to the voltage output of the ohm meter, the current is almost kept on a constant level. Not until the resistance of the potentiometer becomes very low, the current is increasing noticeably. When setting the ohm meter to a lower range, the current is stepping up clearly. A digital multimeter measures resistance by passing a constant current through the device under test and scaling the indicated voltage drop to the accordant resistance value. The magnitude of the current depends on the dialed measurement range. The lower the range, the higher the current passed through the device under test. By using a total of 3 multimeters, we can determine the current and the voltage generated by the ohm meter simultaneously. The display reading of the ohm meter conforms acceptably to the values calculated using Ohm's law. Looks like the ohm meter is compensating the slightly varying current. But the congruency is not perfect. After discovering measurement errors caused by the inner resistance of a multimeter, there is still one question. How reliable are the displayed values of a multimeter? Now all 3 multimeters are connected in parallel to a voltage source. The difference in potential applied to each pair of test leads is identically, hence all 3 devices should display the same reading. As you can see, they don't. If the rotary switch is set to DC voltage measurements, the accuracy of this type of multimeter is given as 0.5% from reading plus minus 2 digits. The indicated value of the right multimeter is 12.91 in the 20 volts range, hence 0.5% of the reading have to be added respectively subtracted from the displayed value. The percentage of reading is plus respectively minus 0.06 volts. 2 digits have to be added to the percentage error. A digit, strictly speaking, the least significant digit is the lowest decimal place of the reading. In the 20 volts range, 1 digit corresponds to 0.01 volts, hence 2 digits correspond to an error of 0.02 volts. Thus, the total error is plus minus 0.08 volts. If the multimeter is set to the 600 volts range, the least significant digit corresponds to 1 volt, while the percentage of reading doesn't change significantly. 1 digit represents 1 volt, hence a total error of more than 2 volts has to be considered. Selecting the lowest measurement range possible reduces the negative effect of least significant digits and gives the most accurate results. As you can see, there are also noticeable deviations while all 3 multimeters are connected in series and the same current is running through the chain, or if all instruments are connected to one resistor. The discrepancy between the labeled resistance value and the reading of the multimeter was highest at the 1 megaohm potentiometer. The variation between the reading of the multimeter and the specified value is not only affected by the accuracy of the measuring instrument, but also by the manufacturing tolerance of the potentiometer. For this type of potentiometer, the given error is 20%, while what the reading of the multimeter is plausible. You might already have noticed the additional symbol at the display of the middle multimeter. That's an indication that the voltage output of the internal battery reached its lower limit and that it should be replaced soon. With the help of a new battery, we can determine the influence of the battery voltage on the reading of the multimeter. While the old battery is connected to the multimeter, 15.71 volts are displayed, and with the new battery the value drops down to just 12.89 volts. This remarkable deviation is indeed caused by the varying voltage output of the battery. The internal voltage regulation of quality multimeters is usually better, hence the voltage output of the battery is a minor issue. Nevertheless, you should never ignore the call for a new battery. At the low budget instruments used in this video, the reading drifts in such a way that the displayed value of the middle multimeter is outside the given accuracy. Let's discover the influence of temperature on the indicated values. The rear cover of the right multimeter is removed so that the hot air blower can heat up the electronics. At a temperature of 15 degrees Celsius, we get a reading of 12.92 volts. As soon as the hot air blower is turned on, the temperature is increasing and the reading of the voltmeter drops to 12.63 volts during the heat up procedure. Even while the temperature exceeds 100 degrees Celsius, the difference in reading stays below 0.3 volts. The temperature stability of this low-budget instrument is not so bad, especially when considering that there was no temperature balance during the heat-up procedure. Nevertheless, there are some reasons not to purchase a low-budget multimeter. An essential criterion is the poor build quality. To be able to replace the battery, two screws with a plastic thread have to be loosened and the whole rear cover plate has to be removed. After a few replacements, the threads are ruined and the cover can't be closed properly. Furthermore, the insulation of the test leads cracked during usage. Both defects concern the insulation of the multimeter, and there is danger to life while measuring high voltages. The cables are very brittle, which is why one of them cracked inside of the test probe, resulting in odd readings of the multimeter. This can become very dangerous if you rely on the reading of your multimeter, assuming that an unknown circuit is not attached to a voltage source, but you simply couldn't detect it. The rotary switch of one device doesn't always snap in place correctly, causing wrong readings. So it is wise to spend some more money and buy an instrument of good build quality. Buying a cheap one and another cheap one and another cheap one creates a pile of rubbish over time. The main functions of digital multimeters are resistance, voltage and current measurements. Another feature of this device is temperature measurement, used before in this video. The test leads have to be replaced by a thermocouple and the rotary switch has to be set to the temperature function. According to the instruction manual, the multimeter is capable of detecting temperatures ranging from -20 to +1000 degrees Celsius. Water with some ice has a temperature of 0 degrees Celsius and the multimeter indicates exactly 0 degrees Celsius. The temperature of boiling water is indicated with 97 degrees Celsius, however that value depends on the atmospheric pressure. A special kind of resistance measurement is the continuity test. If set to this function, the built-in buzzer sounds whenever the resistance is less than 1.5 kilo ohm, hence the measurement can be done without looking at the display. This function is helpful when checking transformers or the windings of an electric motor. If set to 2 kilo ohm resistance measurement, the multimeter can indicate the voltage drop across a forward biased diode. The black test lead has to be connected to the cathode of the diode to be tested and the red test lead to the anode. If the connection is reversed, a single one is displayed. When set to HFE, the multimeter can be used to test bipolar junction transistors. Check out whether it is a PNP or NPN locate the base, emitter and collector pin, which have to be inserted into the proper holes of the socket at the front panel. The DC current gain at the test condition of 10 microampere base current and 3V collector emitter voltage is displayed. The arrangement is just suitable for small signal transistors, and I have used this function in this video for the first time of my life. That's all about the base principles of current, voltage and resistance measurement. Finally, I would like to add some warnings concerning the operation of a digital multimeter. Your intention is to detect the voltage drop across a device in an active circuit with the rotary switch set to DC voltage measurement, but the red test lead is accidentally connected to the 10 ampere jack. Independently from the selected functionality, both test leads are joined through the low resistive shunt inside of the multimeter. If you are unlucky, a device of the circuit under test will end up in smoke caused by this fatal mistake. The multimeter is fused against currents above 200 mA. Nevertheless, the fuse is bypassed when using the 10 ampere jack. In an extreme case, the board of the multimeter will smoke up caused by an operator's error. A circuit can also be shortened if the red test lead is connected to the right jack and the rotary switch is set to current measurement, but your intention is to determine a voltage drop. Now, the multimeter is protected against high currents by the fuse, but probably the circuit under test will be destroyed. Resistance measurement can't be done with the device to be tested being connected to an electric circuit. The multimeter applies a voltage to the test leads, which may cause damage of integrated circuits, especially if the device is connected with wrong polarity. Do nothing but voltage measurements in active circuits built on a board like the breadboard shown here. Be careful, or else you might slip off the pins with the tip of the test lead, which can cause a short circuit. For the reasons mentioned before, you should never set the multimeter to a different function while the test leads are connected to an active circuit. In general, there is. If you are untrained in handling a digital multimeter, you should never examine circuits connected to high voltages. Never touch blank metal in active circuits, because even circuits with a low input voltage can generate high voltages if inductors are placed inside of the circuit. Only use voltages up to 12 volts for your own experiments around digital multimeters. The very last thing to be treated is a short brain teaser. A voltage divider composed of two fixed resistors is connected to a battery with an output voltage of 12.88 volts. For a voltage divider there is the sum of the voltages across the two resistors equals the total supply voltage. Looks like that isn't true for the circuit shown here. We get 8.91 volts for the voltage across the lower resistor and 1.95 volts for that across the upper resistor, thus the sum of the voltages is clearly lower than the output voltage of the battery. The questions are, where are the missing 2.02 volts, and can you calculate the resistance values of the voltage divider? A similar problem occurs when doing current measurements in the circuit shown here, which is connected to a supply voltage of 3.3 volts. The total current running through the circuit should equal the sum of the currents running through the two resistors to the right. Once more, there is a clear deviation of almost 0.4 mA. Now that you have watched the whole video, you should have acquired the knowledge needed to find a solution to the problems. Have a look at at the project page to find out if your solution is identically to mine. Thanks for watching and I'll be back.